In this workshop session, we'll have a look at recurrent neural networks and to implement them using some popular machine learning libraries. We have Mr. Matt O'Connor and Mr. Dhruv Sahi. They are the co-founders of Reboot.ai. May I now pass the time to Matt and Dhruv.
Thank you. Can you guys hear me without the mic, or should I use the mic in the back?
You are using the mic.
But
yeah, it's okay.
Okay. If you can't hear me, just raise your hand, and I'll step closer to the mic. So basically, what we're going to talk about today is recurrent neural networks. For those not familiar, neural network is a new type of deep learning, or not really that new, but a popular deep learning method, right? We're talking about machine learning here. We're talking about AI. Both Dhruv and I's background are in the financial world. I actually worked 3 years for the world's largest hedge fund, Bridgewater Associates, working on their algorithmic trading desk. So I thought I would take some time basically to talk today about recurrent neural networks. And there's no better example of using them than predicting stock prices, right? Running on time series data. So we're going to build a stock trading engine essentially with the recurrent neural network. And if you guys can make this, use it for some money, all we're asking is a little love on the side. So what that's going to look like, right, is just a process where we're getting the data, we're exploring the data, cleaning and preparing it, splitting it into training and testing. For those unfamiliar with that, we'll talk about that. We'll assemble the model, we'll train the model, we'll evaluate the model, and then hopefully at the end of the day, we'll be able to make some profit. So all these kind of steps. The danger with time series data is the actual analysis of it is slightly simple. In all of data science, what takes the most amount of time is the data cleaning, the data preparation. And this is especially true in time series data because it's so easy to accidentally bias your results by basically predicting that you can use future information. Basically saying I can trade on the past data, but somewhere in my data set I grabbed a data piece from the future and put it into the data set that I use to predict the future. So that's a huge risk. It can come up in many different ways, and that's going to be a lot of what we look at today, because that's a major risk with time series. And unlike most errors, where it'll be very obvious that something's wrong, oftentimes with these kind of subtle biases, it can actually be very difficult to detect if anything's wrong, let alone what is wrong.
Until you lose money on it.
Yeah, until you lose money. Yeah. So Dhruv, do you want to start off?
Sure, yeah. So like with any data science process, we're going to get the data. Here we're using quandl.com and calling their API. We're going to look at this.
I mean, I guess, I don't know what the level of expert, but we can just talk about all the libraries too.
Sure,
like we're just using requests to get an API of, so we're dynamically pulling in the data. Sorry, go ahead.
Right, so we're going to dynamically pull in the data, and we have this ticker variable here, which we can change in for tickers to get any kind of stock data that we want. We're parsing this function called getData and using this API. Obviously, we're going to be using pandas data frames to store our data and play with it later on. So we're going to go ahead and use this function called pdparse, which takes the data and uses this IO library to parse it into the data frame itself.
Is everyone familiar with are you guys a data science Python or just general Python, or show of hands, who's familiar with pandas? Okay.
Who's never heard of it? Who thought it was an animal?
Yeah, okay. That's pretty
good, yeah. So we're calling these two recursive functions here, and you getting the stock from XOM. You can look that up if you'd like, if you want to explain that.
That's just the ticker for Exxon, so we're calling the API to get the historical prices of ExxonMobil.
This is what our data looks like. We have obviously a date function, open price, high, low, close. For those not familiar, this is the open price of the stock on that day, the high for during that day, during the trading hours, and low price on that day also. And there's also a thing called the close price, which the price the stock closed at when the trading day ended. We also have amount of volume traded, dividend. You want to explain splits?
I could do it in a second.
Sure.
With adjusted.
All right, go for it then.
So for those not super familiar with financial data, basically, yes, Dhruv described these. These are pretty straightforward, open through close. Those are just the prices on the day. Volume is just how many shares were traded. The dividend is how much, a dividend was pays out that day. The split is a little bit, if you're familiar, stock splits, if you've ever heard of this, a company might issue or double the amount of shares that they have out, or have the amount of shares. So let's say, I think Apple did this not long ago, or a few years ago. Let's say Apple's stock gets up to where it's trading at like $5,000 a share, right? It's just kind of unwieldy. There's a lot of empirical data that says humans are weird and they like stock range. They actually like prefer stock ranges to be in a certain range. So let's say Apple has 100 shares for the whole company at $5,000 per share, right? They can just double the amount of shares that every shareholder has, 200 shares, and the price per share drops by half, right, to $2,500. The total amount value of the company didn't change at all, but we have twice as many shares at half the price. But effectively, if you looked at that on a chart, if you looked at just the close from one day to the next, it would look like the price just dropped 50%. It would look like the price went from 5,000 to 2,500. That's why we have these that's why we have the split and the adjusted, open, close, etc. Those are building in the effect of splits so that we're going to see a continuous price series that we can actually run analysis on. It's not going to, the only thing changing it day to day is the actual trading, not any corporate actions like dividends or splits.
It's just saying basically there are twice as many building blocks to that company.
Yeah, yeah. So that's all that's doing. I guess we can go on.
Yeah, sure. This is how the data looks like from the top. So we're just sort of doing basic exploration, looking at it, the top of the table and the bottom over here, using the tail function in pandas. And we're going to sort on date now. So we're going to see what the first value we have is, just to see where our data starts, We have, as you can see here, it's 1970, 2nd of January. So it's quite a long traded stock, 37 something years. Yeah, it's quite a lot of data we have. All right. So for some basic data exploration, we're just going to plot the adjusted close price by day for the history of the company starting in 1970. So we have quite a few data points, again, about 12,000 days worth of, or trading days worth of data we're going to plot here. As you can see, it's a pretty exponential increase. So if you just invested at the start, you already have been doing well by the end here. It's by buying and holding your stocks, right?
37 years ago.
37 years, yes. It's a very, very long position, but but again, like, you want to explain the log function?
Yeah, sure. So when you look at this chart, when you look at a lot of financial data, very large returns, very long time scales, you can kind of see that this top chart is not super useful. Like when you look at a chart of Bitcoin these days, even looking back 2 years ago, the chart, you can't really read it. I have no idea what these values down here are, right? So the logarithmic scale is just making basically each unit of axis is the same, is a 10 times rise. So instead of like a linear, each of these is $20 in price, the same amount of space now represents a percentage return essentially. So the y-axis just kind of normalizes into a place where we're looking at percentage gains. So when we look at this on a logarithmic scale, it's kind of normalized. It's easier to see when the price is super high now versus when it was super low, basically how it still reacted, and it seems pretty consistent throughout. And one of the main points of this, whenever you're doing data science, you want to explore your data, right? We don't have like a big gap somewhere. We don't have a huge spike somewhere. We're just doing some sanity checking here and kind of getting familiar with the scope of the data.
And this shows the change in price much better than the chart above because that just looks like a continuous up.
Yeah.
All right. So we're going to do some very sophisticated form of dimensionality reduction. It's going to keep the columns that we need and drop everything else.
And the reason we're doing this is because we're going to use price, right, to try and predict price. We're going to use previous prices to try and predict future price.
Find the patterns in prices to see if you can find a mapping algorithm, essentially. But there are some problems with that.
Yeah.
So we're assuming, once we look at this in a normal scale, we assume that a normal distribution is that the average is at 0 and the deviations are on either side of it. But the problem with just price itself is price can never be below 0, right? As you can see that here, there's nothing on the left side of it. But we're assuming this entire distribution when you're trying to predict price normally. So what do we do?
Well, yeah, so what Drew was getting at is in financial time series data, right? And this goes back to what I said at the start. We have to be very careful about how we normalize, how we scale things, right? We want to be normalizing these figures so that we can plug them into our algorithm later. Now, a lot of beginners would just start trying to predict price itself. And there's one problem with price itself. First of all, it's not normally distributed. It's got this weird distribution. It's going to be funky if we try to predict price itself. The second problem is price itself is actually meaningless, right? We're not actually predicting price itself. We want to predict price change. So for example, if a stock is trading at $800, if I'm just trying to predict price itself, it's super obvious. Like one day tomorrow, it'll be somewhere around $800, right? Between 810 or 790, I can know for sure that it's going to be there. It's basically dependent on the previous mean. So we don't want to be predicting price because it's biased. The mean changes over time. We want to predict something that has a standard mean, like represented by all our kind of mathematical statistical representations, and something that is normally distributed. So we want to predict returns. There's one additional complication though, right? We can't just take, I held it today and then tomorrow I had 2% more, so that's a 2% gain. Those type of holding period returns, the type of normal returns people talk about, people look at, people not in finance ever think about, those type of holding period returns are also not normally distributed, right? If a stock goes to 0 tomorrow, what is that percentage return? Negative 100%. But that's the minimum it can ever be, right? Negative 100%. It can never be below negative 100%. So what we're going to do is not take holding period returns, but take something called logarithmic returns. If you just scroll down to the next. And I'll explain this more in a second, but basically, so we can see the chart, this is what a log normal distribution looks like, right? So it much more closely resembles prices. It's bounded at 0. It's got a bunch basically skewed on one side, skewed to the left.
Very skewed on the left, yeah.
And then not much, but a very long tail, which represents in financial data, you have a lot of days where there's small movements, a lot of lower prices, and then you have a few days or higher than a normal distribution on the tails days of large amounts of differential. So log normal distribution more adequately reflects the nature of the data. And the nice thing about this is if you take the log of a log normally distributed thing, you get a normally distributed thing. So if we take log normal returns, because returns are log normally distributed, we now have normally distributed return data, right? And so what that looks like, if we go down, is we're just creating a daily return, a weekly return. We're creating columns where we're taking the log of the adjusted close over the close 1 day ago. So basically the log return from yesterday to today. So not up 2% because I held it, but the logarithmic return, which the intuition here is that as you compound interest more often, right? Compounding interest, we're just talking about if you earn 5% interest, do you get paid that 5% every month, every day, every year? If you compound more often, you actually earn more interest. And the intuition here of why we take logarithmic returns is that it is equivalent to infinitely compounding returns. So it's kind of like the immediate slope of change, which is why in this case where price drops to 0, our return is not negative 100%. The logarithmic return, if our price just dropped to 0, is actually negative infinity. It approaches negative infinity, right? So now we have a normally distributed thing. We have something that represents kind of like the instantaneous rate of change.
So it's almost real time in that case.
Yeah, yeah. So that's what we're doing here is we're taking the logarithmic changes. And we're doing that for the adjusted close. We're also doing that not just daily return, but cumulative weekly return. So the price today versus 5 days ago, which is a week. And then we'll talk about why we do this later, but we're also doing that for the high-low. So the difference between basically the highest high of that day over the lowest low of that day, the change, kind of the range during the day and the range during the week, to give us some sense of like how broadly our prices distributed in that day. What?
This is an equal sign, actually.
-1.
This one?
No, I mean, if you do the return, you should divide and then -1. Right?
Not for logarithmic returns. It's just log of x1 over x0.
It's log of today's price over yesterday's price.
That's the percentage return. If you added 1, that would be, you would multiply that.
Divide it.
Yeah, yeah. So we converted now, we have logarithmic returns.
A lot of warnings.
And a lot of warnings. But no errors, so we're going to ignore them. And so now this is what our data frame looks like, right? We have our original data here, and then we have our computed data on the right.
And because we're looking at the change, we are going to have a null on the first day, because you can't really compare it to anything to get a change in price on the first day. So. Dropping some nulls here so we can actually do our thing.
Yeah, we got to drop those nulls. And just checking out the data. Okay. So now comes some more data cleaning, data preparation. We need to basically, yeah.
When you drop the non-data, you actually drop the whole row or just how do you drop?
We dropped the whole row.
Okay.
And in this case, we're only dropping the first columns where they don't have any values for a week ago, for example, because they're in the first week. So we're just dropping the first
You
week.
don't have a change in price because that's the first time the stock was listed. So.
Yeah. Okay. So now we have, just stay on the head for a second. Now we have basically each row is still each day, right? Each row is one day with a close, with an open, with a percent change from yesterday, with a percent change from the same day last week. What we need is basically a row that represents the time series data that we're going to run. So for example, if we want to use prices from a week ago to predict prices a week ahead, we need a row that has columns for price a week ago, price today, price ahead, right? And so what we're going to do is actually format our data in such a way that we actually get, maybe it's easier to show the output first before we talk about the function.
Okay.
So here we have trailing days is 5, leading days is, or periods, but in this case it's daily data, so days. Leading is 5, and we're grabbing columns for daily return, weekly return, daily high-low, weekly high-low. So what you're seeing here is we're calling this function to time series. We're putting in our data, the columns that we want to do this for, and the number of periods leading and lagging.
If you want to do it for a week, you put in 5 and 5.
Right. And so, oh, sorry, go ahead.
So in a financial world, a week is 5 days, just to make that point, because it's 5 trading days. That makes a week.
Yeah. Yeah, for Bitcoin, maybe you do something different.
Yeah.
So what we have here now is a data frame where each row is basically a time series. It's basically 2 weeks of data, right? We have daily return 5 periods ago. Weekly return 5 periods ago, and so on. Daily return 4 periods ago. Weekly return 4 periods, and so on. So we have each row now has all the data we would need to look at the past, predict something, and then measure our prediction against the future in one row, right? That's the reason we're doing this.
Yeah.
And the function, if you're interested, is just a bunch of manipulation, basically, of taking in the number of trailing periods, and we need to create, a variable for each trailing period, t minus 5, t minus 4, t minus 3, string interpolating the column name, and shifting the columns. It's pretty simple in terms of what it does, but it's very important for time series analysis. If you don't do this step right, you'll get completely garbage results. Yeah.
So one important part or mode of before you do any analysis, before you run a neural network or any algorithm, is training and testing your data, or splitting your data into training and testing. Now it's very important because without doing this, you have no idea if you're overfitting an algorithm, if your algorithm is learning your data too well. So what we do is we take this data and split it into 2 buckets. We keep X%, let's say about 75% for training. We train our model on this. So we create a model on this data we have, and then we take the test part of it and put it inside, or give it the model again and see how well our algorithm can predict test data. So it's essentially you're giving your model that you've trained on a separate data, you're giving it unseen data, so you can actually see how well your algorithm is, how accurate it is.
Right. Yeah, I mean, you've heard probably like horror stories of people in finance. You know, they train algorithms and they think they're going to work in the real world, and they don't. The reason we're doing this is to try and protect against that happening. We're training it on a subset of the data and then evaluating it on a completely new subset of the data that it never saw, so that it can't be biased by the training data itself. It can't basically memorize a time period and just say, I know perfectly how to predict Exxon stock from 1980 to 1990. It can't do that because it's not being evaluated on what it's seen to train.
So you're sort of trying to find its true accuracy, not the accuracy of something you trained on.
Right. And it's a little bit more just messy and complicated, because here we have all these, you know, we have a column for T-5, T-4, T-3, T-2. Our training data and testing is just a little bit messier than normal split. But Drew, do you want to walk through what we're doing here?
Sure. Okay, so where do I start? We're using
well, first we're just splitting 75% of our data goes to training, 25% goes to testing.
We're going to make the algorithm on 75% of the data, and 25% we're going to give it as unseen. We're going to use this mask method to sort of split the data that way. What it does is you write something, like a if statement, for example. You put it in mask, so you get the data out one way, and everything that is not in the first one, you do the tilde mask to get everything else out. It's very high level here. It's getting our number of features here. We already have defined entrail and end lead before, so that's 5 for us right now. And this is the number of observations we have, basically, which is the number of periods times the number of columns.
And then we split out basically training and testing to X and to Y, right? X being what we're using to predict something, and Y being what we are predicting. And so that's why we're also using these like number of columns, number of features, right? The number of columns we're using is 4, and the number of time periods we're looking ahead is 5. So there's going to be basically 4 times 5, 20 columns of future data at the end of every, 20 rows of future data for every, 20 columns of future data for every row. So we need to basically split those out into their separate Y thing, right? We don't want to be using future data in our training data. So this step is also, again, super vital. If you do this wrong, it won't be obvious that you did anything wrong, but your data, your model will be garbage.
Right.
So that's why at the end, maybe we could like print out Y train so people can see it.
Ready?
That's a shape. Can we just print out that? Okay. So we went from, if you scroll up, we went from every single row, right, for different time periods to the future time periods. We went from this to Y train, or Y train, right, which is just, we have the 4 columns in the future that we're predicting. So we dropped out kind of everything beside. We don't need to predict 1 day, 2 day, 3 day, 4 days ahead. We're just going to try and predict the final day ahead. So we're using 5 previous days of data to predict 1 data point 5 days in the future, right? So 1 week to predict a week from now. So that's why you have only 4. You have a list basically every single row. We're going to be predicting basically 4 columns, right? Daily change, weekly change, daily high low, weekly high low. And so that's all we're doing there. We have 75% split into training, 25% split into testing, and then within those we have our X's that we're training on, and our Y's we're training to predict those.
So this is what our shape looks like. We have about 9,000 rows for training and about 3,000 for testing.
Sorry, just when you split it like this, don't you assume sort of uniformity across the data set and ignoring sort of the data, maybe the different time period have different characteristics?
Yeah, definitely. I mean, there's a danger in either assumption. I would argue that it's more dangerous to just take one continuous time period and try to predict another one. In time series data, like let's say the 80s and 90s were, the whole decade was a major bull run, and then you use that to try to predict the like 2000s, which was flattish. That's hugely biased. This is actually purposeful to counteract that bias. It's not perfect, but we're taking random samples so that there's not this larger picture of the market itself biasing it.
So for example, if you train your model on a Lehman Brothers stock till 2007,
right,
and predicted it afterwards,
right, yeah.
All right, so now we're going to assemble the model itself. We said we were going to do a recurrent neural network, so let's do that.
Yeah. Should we just talk about what neural networks are first? We'll just briefly talk about, I don't think everyone knows what a neural network is, so we'll talk about neural networks and then we'll jump back into the code and build our model. So we'll do this just pretty briefly. This is the deck we've done before, so we can just move through it. We don't really need the agenda.
Oh, we're good now.
Okay.
Okay, so why neural networks? Why do you want to use a neural network in the first place? So some quick wins where you want to use them is the universe is not easy. It's mostly not linear, and often has more than 3 dimensions. And maybe not the ones we can see, but there are often more dimensions in your data set than 3. It's very good for complex problems. And also it's good for cases where mathematical models don't exist yet. Also, it's very flexible. It's quite varied, and it's data type agnostic, which is a lifesaver often.
Yeah.
It saves you a lot of cleaning. And also, you can put in any type of data you want. So anything you can sort of put into numbers, you can put in. It's also self-teaching. What that means is it doesn't have to be explicitly programmed. You can sort of give it some parameters starting off, point it at something, and it'll try to solve it for you. So it's used for a lot of classification and prediction regressive problems. And as it goes through, it minimizes error, which we'll talk about in a little bit.
Yeah. We could just skip. I mean, they're not like absolute beginners.
Yeah.
So, well, actually, go to the one before. So just real quick, one of the things like neural networks are good at, reducing basically dimensions, taking 2-dimensional data and basically thinking about it in a higher dimensional plane, right? Which is, if you look at this, it starts out on 2 dimensions. It starts out impossible to use a straight line to classify only red or only blue. Neural networks, this is kind of a visualization of the intuition of what it's actually kind of doing, expressing things on higher dimensional planes and teasing out relationships that are not obvious to human beings.
It can squash dimensions or take them out, find a linear fit in that dimension, which isn't linear in this dimension, and then bring you back the results.
Right. Okay.
This is another good example, actually.
Same
so,
thing.
Yeah. All right.
Same thing. Okay, so I think image recognition is the most obvious or most relatable example. So example, how do neural networks work with an image recognition? You start out with a picture, let's say Will Ferrell. You basically, all neural networks do is just converting data, whether it's time series data, image data, any data, into vectors. What that means is we basically, in the case of image recognition, take each pixel. It has a certain value, right, related to its lightness or darkness, a numerical value that the computer is using to represent that pixel.
For example, if it's completely white, it can be 0, and if it's completely black, it can be 1.
Yeah. And then we are just converting basically each pixel into a vector, basically how dark or light that pixel is compared to the ones that surround it. That is what is being done here. This is not the neural network itself, but it's processing up to the neural network.
It's the intuition behind it, right?
Yeah. So that picture, that image, becomes basically a vectorized
vectorized information data set.
Right, a feature set, if you will. And then that, for example, is how facial recognition algorithms work, right? You reduce a picture down to that numerical vector representation, and then you compare how well does it match up against just a general template, right? You're just training, does this data match this other data? One vector of numbers match this other vector of numbers. If it does, I know I've just detected a face. So that's, for example, like how neural networks would run on image processing.
Right. And
we'll go much more in depth really quick just to walk through it. That's fine. Just like anything in data science, neural networks are just basic algorithms that minimize error. Right? It's trying to predict something, it measures how well did I predict it, it quantifies that, and it learns to minimize the error over time. In that sense, it's no more complicated than linear regression. Right? The simplest possible thing you can imagine. It's the same exact approach, just minimizing error. Keep going. So, yeah, I guess this is worth it.
All right, so also the intuition behind this is, like, let's say if I ask you which one is a dog and which one is a cat, you're able to tell me immediately. But that's the beauty of the human brain. But if I ask you how you know that, you may look at this and say, cats have larger ears and whiskers, dogs have noses that come out. So it's sort of the similar steps that a neural network would learn. But the idea is you don't want it to learn a cat or a dog from the images you gave it. A really successful convolutional neural network, one that's really good, will learn what a cat or dog abstractly is. So I don't want to give it an image that I've already given it and say, that's a dog. It's already learned that, but I want to give it an image of a different dog in a different context, above a mountain, in snow. And then it's still being able to recognize that it's a dog. So it's more about learning what a dog is or what a cat is rather than just what the data is.
Yeah, to that point, this is how neural networks were created or arose, right? When the human mind sees these pictures, you kind of see multiple things at once, right? You see, they're all furry animals. They all have pointy ears. Some of them have longer whiskers. Some of them have bigger tails. You see these kind of like hierarchies of things, right? They're all furry. Some of them are this. Some of them are this. There's subsets and supersets. That's what your mind is seeing. A neural network is basically an attempt to take that biological process and turn it into a numerical, an algorithm, essentially. It's not necessarily like a mathematical formula that someone discovered or came up with. It started from this kind of intuitional attempt. So if we go on, here's an image example. It's actually very hard, right? For the same reason, our minds have trouble with this one. All the things are crispy or crunchy, they all have the same texture. This just drives home the point that we're not seeing dogs and cats. We're not seeing chicken and dogs. We're seeing features, right? We're seeing colors. We're seeing textures. And those features, color and texture, combine in our minds to produce the final output of, oh, that's a dog, or oh, that's fried chicken, or oh my God, I think I just ate a dog.
They do look very similar, though, with the crunchiness, but.
Yeah. So this is just like a representation of how that might happen, right? At some level, a neural layer in your mind is seeing the color brown. Then there's another one that basically neuron fires, and a neuron near it takes that input of firing and runs it through its own process and says, I'm detecting, given that you saw brown, I'm detecting some light and some dark brown. I'm going to trigger, because that's what I do. Like, this neuron just triggers when it sees light or dark brown. Then the next neuron that receives it, it looks for texture, right? Just these features that our mind sees, right? We see brown, we see texture, we see color. That fires, and basically it's this layers, this sequential pattern of neurons firing, speaking to each other, that add up to, oh my God, it's a dog, right? It's not that your mind immediately, like every cell in your mind knows it's a dog. It is this kind of network of neurons speaking to each other. And how confident they are in perceiving their relative thing that they're looking out for determines how much they fire, how strong the signal the signal they send to other neurons is. So what does this look like mathematically versus biologically, right? We just saw this basically in the mind. The reason we just had trouble classifying that image, we just saw brown, we saw crunchy, we see those features. Basically a neuron would get that input and it would see brown and it would fire, and it's connected to other neurons, right? And that next layer of neuron, oh, you saw brown, and I know that when you see brown, I look for this. Did I see this? No, then I'm not going to fire. Did I see this? Yes, then I'm going to fire, right? It's just this network of connected nodes, essentially. That's all a neural network is, just making that into a mathematical process, an algorithm, right? We're going to have inputs. They're going to go into some kind of summation function. They're going to run through some activation function, which is basically just that threshold measure of how sure am I or not that this thing just happened. And then we're going to pass that along to the next neuron, and guess what? That value becomes the input for the neurons in the next layer. That's all it is.
That's how the learning happens.
Right. Yeah. Well, back propagation. So that's where basically the deep learning comes from. You have these deep layers. You have these hidden layers, it's called, in neural networks. So we have the inputs, which in the case of image recognition, right, might be just those pixelized values. So a number between 0 and 1 representing each pixel's lightness or darkness. We kind of, this is a fully connected layer, so we multiply those by weights, and we add them all up into the next hidden layer. We repeat that process, and we're just propagating forward until we get to an output classifying, is this a 0 or 1, is this a human face or not? So if we just walk through a really simple example, step by step. Go to the next slide, actually. Next one. Next one. go back to that one in a second.
Where do you want me to go?
Keep going. Okay.
All right.
So, just the math behind it, like this is what's so amazing about neural networks. The math behind them is like absurdly simple.
It's primary school mathematics,
Yeah.
really, yeah.
Just go to the next slide. Okay. So imagine like we're trying to predict the price of a house, right? And we have one input that is kind of like the size of the house, and one input that is the quality of the house, some kind of quality metric about the house, right? How good the neighborhood it's in is, or whatever you want. We don't really know as human beings what is the perfect way to think about squashing like size of a house and quality together, right? Do we take like 30% of the price plus like 70% of the quality times some scaling I don't know.
We don't know how to value each thing, right?
Yeah. So what a neural network is going to do is basically combine these two vectors into a value that basically combines two dimensions, right, into a single vector that can say the quality price, the quality size of the house yields this price. So that's the intuition of what we're about to do. How that actually works is we feed in the values. Let's say they're 1, just as here. These numbers are weights, so they're randomly initialized at first. Literally just pick random numbers in a range. We don't need to get perfect at the first because the network is going to update these and learn over time. So we have weights, and in a fully connected layer, each input layer is connected to its output. So we've got 3 connections per input. 1 times 0.2 plus 1 times 0.2 plus 1 times 0.8, the 2 connected to this one, will sum to 1, and so on for 1.3 and 0.8. We literally just multiplied and added. This is where the activation function comes in. Next slide, I think. The only kind of complication is that we just put that number through an activation function. What is an activation function? Again, the intuition is we're trying to get how sure we are of the signal we just saw, right? This process is going to normalize it, it's going to compress it to a given range, and depending on the activation function you pick, it'll do certain behaviors for certain use cases. So for example, in image recognition, in convolutional layers, if you're familiar with that, you'd want to use something like this, where it kind of it's either an all or nothing kind of output, because you're trying to find edges or something like that, right? All I'm trying to say is there's different activation functions. They're better or worse for different use cases.
Right, yeah.
But the intuition is just, sigmoid is like this beginning one, very popular one. It's just a function. You feed in x, and f of x is some value, and sigmoid is useful because it compresses numbers between 0 and 1, for example, and that lends itself directly to being interpreted as a probability. So that's why, for example, those type of activation functions would be popular or useful.
So in a way, it's giving every node in the hidden layer sort of a vote of how sure it is that it should be activated over the other ones.
Right. Yeah. And so all that we've just multiplied and summed, we just feed it through the activation function. So 0.8 into this function is 0.69. And then guess what? We just repeat the process for the next layer. Multiply 0.69 by 0.9, and add that to this times that, and this times that, and that's our output. That's all that's basically happening in a neural network. It's no more complicated than that. I mean, it's a little more complicated, but that's basically generating a prediction, right? We have now an input, and we have weights, and we have a prediction. The network now has to learn, which is the complication. We have to be able to quantify the error, basically how much we were off by, and then we do something called backpropagation, which is just literally what we did in reverse. So instead of putting inputs through, we're taking the amount of error that we just quantified and putting it backwards and updating our weights. Basically, each weight will get updated kind of proportionally to how much error it created.
So if this had a lot of error, for example, it may become much smaller or much bigger.
Yeah. So that is the mechanism by which the network learns. These randomly picked weights change, and it just runs a bunch of iterations until the outputs are very close, or as close as it can get, to the predictions. Yeah, I think that's pretty
much it, yeah.
Yeah, okay, we can go back to that. Notebook. It's not up for some reason.
Weird.
So that's what a neural network is. Thanks to Keras, which is built on TensorFlow, it's like 2 lines of code to implement this, which is amazing. But you can see why, right? Like the math is actually incredibly simple. The concept often turns people off or confuses people, but the math inside of it is like, yeah, a 6th grader could literally build a neural network.
Right. Minus
Okay.
the error functions.
So Keras is incredible. We're just importing Keras here. We're importing something called sequential, dense, and LSTM. What does that mean? Sequential is just a sequential model. We're going to have multiple layers in our neural network. Dense, what does dense mean? It is just a fully connected layer. All the layers we just looked at, where all the nodes are touching the next layer's nodes, that's what a dense layer is, a fully connected layer. That's all that is. LSTM is a little bit more fancy. Long short-term memory. It is a form, it is a subset of a recurrent neural network. There are multiple different types of recurrent neural networks. LSTM is a subset of that. And if we go down, just look at this diagram really quick. Essentially, rather than only using the previous layer to predict now the next layer, we're also using nodes within the same layer. So it's taking in basically the data point from one time ago and also the memory from basically the same time, right? So if we're t minus 3, we have an input from t minus 4, but we also have an input from t minus 3, the next variable.
Right.
And so it's basically creating memory that it's passing along horizontally vertically instead of horizontally through the network.
So it's the nodes in the same layer are sort of talking to each other and deciding what is important to remember and what it can forget, put it that way. Yeah.
So in the context of stock prices, this lets us say, okay, conditionally that 5 days ago it changed this way, and conditionally 4 days ago it changed this way, and conditionally 3 days ago it changed this way. What's our prediction now if it changes? Rather than independently, okay, it changed this way 5 days ago, what does that mean for 5 days from now? And then independently, it changed this way 4 days ago. What does that mean for 5 days from now, right? We don't have as much information as if we have these talking to each other and saying, oh, 5 days ago you did this, well, I did this 4 days ago, right? We're now capturing more information. We have a memory beyond just one data point at a time. That's all this is doing. And so if we scroll up, building that model with Keras is incredibly simple. Model that equals sequential, we're just creating an empty model. Model.add LSTM 50, return sequences equals true, input shape, xtrain shape 1. Break this down one piece at a time. LSTM 50. We're just creating an LSTM layer with 50 nodes, right? 50.
They have a vertical thing with 50 circles in it, visually speaking.
Yeah. Return sequences equals true is just that it is going to return vectors of basically sequenced vectors that is going to pass to the next layer. We actually have 3 layers of LSTM. So we only need this if we're passing to a next LSTM layer, but we're using this here because we have 3 layers of LSTM and then a dense layer. Input shape is equal to xtrain shape 1. That's just saying how much data, how many inputs am I taking in to the first layer, right? So we have 6,000 rows. We're just getting how many columns do you have per row, and then it's going to run 6,000 times essentially. And so we have LSTM, 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 and then we have a dense at the end, which has 4 nodes. So each of those nodes will correspond directly to a variable that we are predicting, right? It's not a coincidence. We're predicting daily return, weekly return, daily high-low, weekly high-low. So the output of those final 4 nodes from the fully connected layer will be directly interpretable as our predictions for those relative columns. We're going to compile the model. This is just basically how we measure loss and how we optimize how much or how fast or slow the model learns. Basically, how much is it adjusting each time it has error. If you adjust too much each time, you might never reach a good prediction, right? You're overreacting each time. My error is too low, or like my price is too high now. Oh, my price is too low now. Oh, I'll adjust a bunch. Oh, my price is too high now.
Be alternating between those two.
Yeah, if you adjust too little, you might never reach a good prediction. Your price is too high, 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 your price is too high. You'll never get to a good prediction. So again, the devil's in the details. Like all these type of things, especially with time series data, are incredibly important to get the small details right. So we're just printing out a configuration of the model, just a list of the parameters, basically details about every layer, what the activation function is, what bias we're adding, what the model is doing here, just so we can see basically what is happening in each layer. And then we've already trained the model, but this is the actual training here, just model.fit, feed in our training data. We set the number of epochs, basically the number of times it wants to run, batch size, how many units is it going to train per run. Rather than running on all 6,000 data points, for example, it's just going to run on 72 per time because that's going to be a lot faster to break it up into pieces without much sacrifice in accuracy. And so you can see basically we just printed out the loss and the validation loss each iteration. So over time, there should be a chart at the bottom, yeah. So you can see what the error looked like as the model learned. So it started out really high, as one would assume, because it didn't know anything. And then as it trained, it got better and better and better, and the error dropped. And we have the training error lower than the testing error, right? Because it's training on the training data. It's like 99% of the time, unless your data is artificial or something's messed up, your training error will be lower than your testing error. And
you
then
see that, like, as it learns, the error decreases rapidly.
Right.
And then sort of plateaus towards the end when it can't.
Yeah, I mean, maybe we're at risk of overfitting here, right? Like we have diminishing returns at 30 iterations. Maybe we should just run 30 iterations because we're at risk of overfitting and basically having a model that only works for data it's seen before. And then when we go out into the real world and start trading, we're going to lose tons of money. So,
Probable.
we have our model, we have our predictions. The other devil in the details, right, is like how do we actually, what does this mean? How do we evaluate is this good or not? How do we all retire and start a hedge fund? There are many different metrics you can use to measure this, right? So we ran through a bunch. The first all we did was just created the predictions. So model.predict x test. So now that the model is trained, we can use it, just generate predictions for all the testing data. And then we just created a pandas data frame which has our realized daily and weekly returns and our predicted daily and weekly.
So actuals versus predictions.
Right. We are then just trying to quantify some basic things about how accurate this was. There's no real right or wrong answer about how to do this, but we did quite a few. So the first is we just wanted to see are we any good at predicting things? When we say price will go up 1%, is it going to go up somewhere between 0.5 and 2% essentially? Like, are we anywhere close? And we only got 4% of direction and magnitude of days right. The next thing we just wanted to look at was when we say price is going to go up, does it actually go up? Anything above 0, does it go above 0? Anything below 0, does it go below 0? That, I mean, we got above 50%. You laugh, but you have, 0.53% would be a phenomenal algorithm, right? Like, when you have a ton of money and you have, this is just on one stock, right? If we ran this for 500 stocks, imagine, and we just had to pick one stock a day to trade, right? These financial players, these major hedge funds, they don't have much higher than this accuracy.
And every
they just lever
small
up and make a
change in
ton of
accuracy,
money
yeah.
on the smallest advantage. Right?
Smallest advantage you find could make you millions and millions if you have the capital to back it up.
This is an advantage over just flipping a coin. And statistics show that basically most managers are worse than just flipping a coin.
It's not wrong.
So then we looked at the correlation between basically our return stream and the actual return stream, pretty low, 20%. And then we wanted to just look at let's do some trading, back test simulation. Let's have a portfolio and measure how much money we would have made. So, okay, the reason we did all this thing with the weekly high-low and the daily high-low, let's say our prediction said that the price is going to go up 5% tomorrow. Should we buy? The answer is you don't know. Is 5% high or low? Has the price been changing 50% a day? Might we risk our entire portfolio, right? With Bitcoin, if it says the price is going to go up 10% tomorrow, but it just dropped 50% yesterday, is now really a good time? Is that really a high risk-reward profile to invest? So we looked at basically predicting the high range, the high to low range as a way to kind of quantify Not only how much return do we expect to make, but how much risk are we taking on? Again, this is hugely important for financial time series data. So we wanted to do that so that we have that measure of, relatively speaking, we think it's going to go up and it's going to be low risk. So we should buy right now, right? Without knowing risk, reward means nothing. So all we're doing here is generating a risk reward profile and saying, like, when we have the best 5% and the worst 5%, let's trade those days. So the best 5% will buy, the worst 5% will sell. This is just some formatting to make that happen. And then we basically, I've scattered these in the thing below. And so this is what it looks like now. So basically, these are our worst days, these are our best days. Here's just a linear fit of these days. And then if we actually, I just built a portfolio simulator basically. If we start with $1,000 in a portfolio and we have our HODL portfolio, which is just buy and hold, basically how much return would we make at the end of our, if we traded this strategy that we just generated? And I don't remember off the top of my head, but what was the
Average annualized return?
yeah. Why is it printing out every time?
Because you said print in a for loop. Yeah.
That should not be indented.
All right.
There we go. So our annualized return was about 4.6%. And if we, that might be good, might be bad. If we look at basically how is this compared to the HODL portfolio, not as good. But there's a major caveat, right? This is not correlated. This is not a correlated revenue stream to buying and holding. This is an uncorrelated revenue stream. So if I'm an investor and my only option is just to buy the stock market, I'm always looking for things that are uncorrelated so I can diversify my income. So we have a strategy now that generates a positive return, generates 4.5% annualized returns, and is uncorrelated to the general just buying and holding the stock. So
Doesn't do too bad either.
yeah, that's not that bad. Maybe we should retire and start a hedge fund. So yeah, so that step 2 matters a lot, and I just wanted to do one more thing in the calculation above the chart. Yeah, the profit. The other thing is, again, it's actually easy to build a model that will make you money. Another thing people forget, and this is again the details matter so much. Another thing people forget is the trading fees, right? You have to pay commission. You have to pay slippage costs. If I'm buying a ton of stock, the price is going to go up on average while I'm buying because I'm pushing the market up. So you have to build in assumptions of fees to every model you ever make. And so here we're assuming fees of 20 basis points, which is just 0.2%. Basis points is a more granular measure of percentage. 100 basis points is 1%. 50 basis points is 0.5%. So we have fees of 20%, and we're building that into every time we place a trade, we are modifying by our fee modifier, so we're paying a 20 basis point cost for every trade. You have to use that, otherwise you're going to get great results, and then you're going to trade, and you're like, I'm not making any money. What's happening?
You're going to be out of your money in about 3 days,
Yeah.
probably.
So especially if it's high frequency trading, you're going to burn through your cash. So again, so time series data with recurrent neural networks. Recurrent neural networks are awesome, but there's so much importance on cleaning the data, preparing it correctly, building on all the assumptions, testing it, and if something looks funny, if something looks like you can retire tomorrow,
Investigate it.
probably messed up somewhere.
If someone tells you they have 99% accuracy, they don't.
Yeah. Anything else you want to add?
No, so profit? Maybe.
Maybe.
I mean, just when you guys are testing, why don't you just change another stock instead of ExxonMobil? It's changed to
Yeah.
another stock and test how it works.
We've done. Oh, so you're saying evaluate the model on a completely different stock? Yeah. So that's another methodology. That has an assumption though that 2 completely different stocks behave the same way, which may or may not be true. But there's no reason you can't try both methodologies and see like does one work better than the other? Does one have higher risk than the other? Yeah. Any other
Questions?
questions? Yeah.
Would you use anything else other than LSTM?
Yeah, I mean, a lot of research now is saying that some methods of convolution can actually be just as good or better than recurrent neural networks. Haven't used that too much, and then capsule networks like just came out practically. So there are, I mean, this field is evolving every day. So yes, I would try other ones.
But also, I mean, we haven't really optimized this model too much, right?
Yeah.
We're just looking at previous price to predict future price. There's so many more things like volume we can add, for example. Yeah.
But you'd have to be careful about how you normalize volume.
Right.
Like feature scaling doesn't work in time series data.
Sadly.
Yeah. I guess we can.
Yeah. Okay.
Yeah.
I guess so, yeah.
Our retirement portfolio is this notebook.
Don't forget the 50-50.
Yes. All right. I guess that's it. Oh, yeah, one more.
How did we split the train test here?
We just basically split up weeks at it, so separated weeks out. So we're pulling weeks out. If you think of this chart, we're just like pulling random weeks out. This week is training, this week is testing, this week is training, so that we don't have a huge like train on 80s through 90s a bull market and then predict like a bear market type of problem. Is it perfect? No, no method is perfect, but we're trying to avoid that assumption.
We're inherently random sampling.
Does that answer
weeks,
your question? Okay. All right. Cool. Okay.
Yep.
Oh, yeah.
First, I see each row you have 5 days.
Mm-hmm.
Right? And
Yeah.
You just invent your independent sample.
What? Sorry?
That's our input, yes.
Yes, your input.
Yeah.
But as you in your LSM or LN larger memory model.
Yeah.
Actually, your last sample, I mean current sample, is the last previous sample.
Right.
But these 2 samples may be they may be in the same period. I mean, because at first you sample, when you get the sample, these 2 rows, maybe there can be some gap in gap period.
I don't understand.
I think you're trying to say I think you're trying to say that if you take random weeks out and try to predict weeks afterwards, you're gonna then do that, right?
We take random weeks out.
So if we take 1 week out, we predict the next week afterwards, right?
Yeah.
Yeah. So no, we don't really have a gap there, because if you take this week out, for example, we're trying to predict next week's closing price. There's no gap in the middle of trading.
Sorry, I mean, because when you use RS model, actually you use previous data, right?
Yeah.
But this previous data maybe is not so previous. Maybe last period. Maybe it's 3 periods ago.
Yeah, so we
there-
we looked at the data though. There's no gaps in the data, right? It's continuous data. It's from a good data source.
It's fully complete.
Yeah.
So I don't think you are actually use the RS model.
We shouldn't use LSTM even?
No, I don't know you shouldn't. Because I think there is a gap in the days. So
There's no gap in the days. It's trading period. 3 trading periods ago. 2 trading periods ago. Okay.
Sure.
Okay.
Yeah. Oh, should I ask you?
What?
This is what Bridgewater does.
No comment.
Highly secretive, I guess. All right, let's do that.
Are we done?
I think so.
What happens now?
All right, thank you guys. Yeah.
Thank you. We'll have to coordinate with the writers.
You put in GitHub, I guess.
Yeah, we can put it on.
Thank you, Matt and Drew. This is the end of today's talk sections. Let us invite the organizer of PyCon Hong Kong, Dr. Hagen So, to say a few words. Hagen, please.
How do you mean by that? If you're predicting using 5 days of trade, you're predicting something in the future with weeks skipping in the middle. Also, we're not doing that.
Oops, I need to get my back down. So time passed really fast. I wish there are even more talks, but yeah, it's now finished. There will be a video to conclude everything, but it takes a little bit of time to set everything up. And of course, we also have to thank all our sponsors, and then the logo of the sponsors are also coming up. Yes, and please bear with us a minute. Yeah.
唔係佢因為
哦，OK，咁啊，咦？唔係喎，你駁咗，唔係我講住啲 sponsor 先啦。嗱，你幫我駁咗已經有個，咦？咩事？咦？睇下先，我個唔係，哎呀！哦，咦？你幫我 scroll 個 sponsor。Okay, so our sponsors, the first one would be the Python Software Foundation. Is it on? 唔關事啊。
撳咗㗎啦。
Display。
呢度唔係啊！呢度啲嘢轉過嚟㗎，呢度啲嘢
揾唔到喎。
唔係呢度啲嘢改過嚟㗎，呢啲嘢唔等先。
咦？就係你想我用啲嘢變
得啊！唔係俾人落完到你。咦？
唔係啊，Hagen 個電腦係咪 virtual 上去？
冇啊，唔關事。
有啊，都係
關事一啲。
呢度咯。
換 HDMI。換咗佢。
得唔得啊？因為上次咧 HDMI 搞掂嘅。啊！一樣㗎，有乜分別啊？唔使啦，好啦，睇咗啦。啊，得你俾少，等陣先啊，開到 YouTube 先。誒，你去咗？得啦，Sammy 嗰部嘅。誒，我呢部都得嘅咯喎。你 play 咗個 video 先啦。唔係，淨係我講先啊。你講下我哋講住先啦。講住先啦。Okay, we will play a short video. Hey. Hả? IE or Edge？IE 嚟嘅呢個。係咯，係咯，不過呢部學校機嚟㗎，大家忍耐啊！So without everyone's participation, we would not have PyCon 2017. And then we are very grateful for our sponsors, including Python Software Foundation, and they help to subsidize every PyCon in different cities and places in the whole world. Everyone's participation. We would not have. That's interesting. And we are for the general sponsor. For our sponsor, it's a company that works on data and so on. Every PyCon in different cities. Okay, don't worry about that. Another voice of mine. AXA investment managers. And and MySQL. Okay, and okay, so that is and okay, so there is actually one more thing we would like you to help. That we are still thinking about what to ask you all, because there will be a post conference survey, and then we will email it through the Eventbrite system. And I would like to ask all of you to give us feedback, and also for our organization, we would also like to know how we could help you all, because we know that for good Python programmers and people who know data analysis and AI, I think the industry is still short of people. So is there a way that we can help? So please tell us your opinion on how we can have a better PyCon next year, and also generally what type of event do you like and how we can help. So that's basically what I want to say. And any more thing, Sammy? Oh yes, I've forgotten to thank City University. Yes, to have this great venue, and then also the City U App Lab. They help us a lot, and then we bother them a lot actually, and then yes. So basically, that's all. Oh, yep. Forgotten the patrons and those people that donate to us greatly. Dick Dung, Henry Law, Greg Griffith, Lawrence Law, Leo Chiu, and Rossetti Huang. Yep, and then there are individuals that contribute in terms of money, and some of them help as volunteers as well. Yep, and also of course we have young people here, other volunteers, the video team, the MCs, and we are also very grateful for them.
Yeah, thank you. Yeah. Thank you, Hagen. Yeah. So and thanks for your coming as well. Yeah. Have a great day. Yeah.
Yeah. Oh, 唔該曬個。